Okay, in the last lecture, we talked about the Pearson correlation coefficient. This is just a reminder of what the Pearson correlation coefficient is. Basically, we're looking at something very similar to correlation, except it's effectively a covariance sum where we've subtracted the mean of the data from the data set. So we basically have x minus the mean of x and y minus the mean of y, the sum across those. Normalized to divide by n minus 1, and then also normalized for the variance of x and the variance of y. And so this is known as the Pearson correlation coefficient. It gives us some idea of the relationship between data sets. If we remove the means of the waveforms, then the Pearson correlation coefficient can just be obtained directly from the correlation equation. This makes the correlation value equal to +1 when the two signals are identical, and -1 if they're exactly the opposite. So Pearson correlation coefficient, or just correlation coefficient, is going to imply that this has been normalized. Correlation is generally used to mean normalized or unnormalized correlation. So correlation is a more general term. Correlation coefficient refers to this normalization process. So here's an example of the Pearson correlation coefficient between two waveforms. So we have waveforms x and y. Your author has provided a number of dot and mat files which contain the data in the examples that he provides, as well as the data that he requests for various homework problems. So this particular example, we're asked to find the correlation, the Pearson correlation coefficient between these two waveforms. So let me go to screen view. So here's the code for example 2.7. This is included in the Dropbox file that you were invited to. There are too many M files for me to post on Blackboard, so I have a Dropbox folder. You should have received an invitation to join and view, and if you have not, then you need to contact me and I will re-invite you. I believe the email comes from Dropbox. Okay, so we want to load the file and find the unnormalized correlation using the example using the approach in example 2.5, and then subtract the means of each signal before we correlate it. So when we subtract the means, we're basically going to this Pearson correlation coefficient. So we load the signals. So when you have a dot and mat file, you say load, and then that brings the signals up in memory. First of all, we say that our number of points is going to be the length of the vector x. And then here is where we're finding the basic correlation. So we have x minus its mean times y minus its mean, point by point, and then taking the sum. And then to get the Pearson normalization, we divide through by n minus 1 and the square root of the variance of x times the variance of y. Then we can entitle this correlation, and the Pearson correlation coefficient turns out to be 0.75, indicating that there is some similarity between the waveforms. So let's go back. Okay, so some similarity between the waveforms. Most of the similarity, I think you can see, comes from the fact that you have a waveform above 0 here that then transitions to a waveform below 0 here. But are you surprised that the correlation would be as high as it is between these two waveforms, given that they're relatively dissimilar in shape? Okay, the covariance matrix. So when we have more than one signal, basically the covariance matrix is going to show the variances of each signal on the diagonal and the covariances on the off diagonal. So for example, if we have a single signal and we want to find its variance, then the variance of signal 1 is in element 1, 1 of the covariance matrix. The covariance between signal 1 and signal 2 is in position 1, 2 and in position 2, 1. So this is a symmetric matrix. So sigma squared of 2, 2 is going to be the variance of signal 2. and so on. So basically, we're showing the covariance matrix shows the signal covariances. In this case, X is a matrix that contains the various signals to be compared, and the signals to be compared are in columns. So if you have a 64 channel EEG, channel 1 will be column 1, channel 2 will be column 2, channel 3 will be column 3, and so on. Usually, when data are acquired, signals come in rows. So what you often have to do is you often just have to make the columns the rows and the rows the columns of that matrix. So this matrix of correlations is similar to the covariance matrix. It's just that instead of covariances, you have as your matrix elements the Pearson correlation coefficients. So the diagonals in the correlation matrix are all 1 because that would be the correlation of the signal with itself. And then the off diagonals are the cross correlation of one signal with another signal. So in MATLAB, you can compute that using S is covariant of X, where X is a matrix that contains the various signals to be compared in columns. So as an example, determine if a sine wave and a cosine wave at the same frequency are orthogonal. And if sine waves at harmonically related frequencies are orthogonal, and harmonically related would be 2, 4, 6, and so on. And so in other words, the coefficient multiplying time is a multiple of the other coefficients. Also determine if sawtooth and sine waves at the same frequency are orthogonal. So we're going to generate a 500.1 second time vector, and we're going to use that to generate a data matrix. And in our data matrix, we want to have 1, 2, and 2.5 hertz cosine and sine waves. And then we're going to look at covariance and correlation routines and display the results. So here is the creation of cosine and sine. Here is 2 pi t, here is 4 pi t for 1 hertz and 2 hertz. And then we're going to solve for a covariance matrix and a matrix of correlations. This is available in the Dropbox folder, the M file that generates these data. So we won't dwell on that a lot. Okay, so what happens is the covariance matrix and correlation matrix. So here's the covariance matrix. You notice the diagonals. Here's the correlation matrix. You notice the diagonals are all 1. You notice all the off-diagonal elements are 0. So that means they are completely not correlated, which would mean they are indeed orthogonal. So there's a mathematical dissimilarity between sine and cosine, and that's a problem when you're trying to generate patterns, such as the oscillatory characteristics of a sine wave. So correlating a waveform with a sine wave might make you think it doesn't exhibit sinusoidal behavior, because as you've seen, we can have a perfect cosine wave, and because it's a perfect cosine wave, it would be completely out of phase with the sine wave orthogonal to it, and we would get 0 as our correlation. So the way to circumvent this is to use the cross correlation previously mentioned to assess the correlation between the two waveforms at many different times or phase shifts. And cross correlation then is most likely to find the best match between two signals. So for example, if we come here and we shift one sine wave with respect to another, there will be times when we have a very high correlation when the two waves are aligned, times when we have 0 correlation when they're out of phase, and times when we have negative correlation when they're 180 degrees out of phase. So you can see that this tells us then kind of what the relationship is between the two waves, and it also tells us at t equals 0 that they're completely uncorrelated, and at t equals roughly 1.5 seconds there's a maximum correlation. So you could sort of back calculate then what the phase shift is between the two waves at t equals 0, because it takes like 1 point however many seconds to reach your maximum correlation of 1. So here's the equation for cross correlation repeated where you have your y of n and then you have your x of n plus k, where x of n is your probing function and it's sliding across y. K is the actual time shift. And that's because we're not in time here, we're in discretized units, we call this a lag. And the lag is always going to be less than or equal to plus or minus n. So if the signals were originally time functions, then the lags are converted to time shifts, can be converted to time shifts in seconds. In MATLAB, let me go back here. Looks like I jumped ahead quite a bit. So you don't have to have the same length here. So in MATLAB, you can implement cross correlation by using this routine xcorrelate, where x is your x and y are your waveforms, and then maximum lags gives you some idea of where you want to start and stop your cross correlation. If you're using MATLAB, you have to have the signal processing toolbox to use the cross correlation function. AXCore is a MATLAB implementation of cross correlation that your textbook author has written in case you don't have the signal processing algorithm. And here's the syntax given for that. Cross correlation operations usually scale by 1 over n. In this routine, it uses scaling that gives Pearson's correlation coefficients, which means 1 over n minus 1. So this cross correlation is going to range between plus and minus 1. You can get exactly the same results if you take that xcore function and divide by the square root of the variances. So here's an example that your author does on cross correlation, where you have two waveforms, x and y. They're recorded from two different neurons in the brain with a given sampling interval. It's thought that they're separated by one or more junctions that would give a delay to the signal. So you want to plot the original data, determine if they're related, and if so, what is the time delay that's between them. So we want to take the cross correlation between the two signals. If we find its maximum, then that would give us some indication at what the time shift was when the maximum occurs. That'll tell us, first of all, if they're related, and secondly, what the delay was. So we're going to load neural data, determine our sampling frequency, determine our time vector, and do a subplot of the original data sets. We then compute the cross correlation using AXCore and do another plot, and then we're going to plot the cross correlation. So what the subplot command does is it basically gives you two graphs on one page, and you can see what the output will look like on the next slide. Then we want to locate the maximum, so this max value will find the maximum value of the correlation. So the max operator gives you the index of the maximum value. If we want to find out what time that occurs, basically we look at this command, this value max shift. So lags finds the value of the point at which this max shift occurs. So what lags does is, let's say the maximum value occurs at n is 7. Okay, this will identify 7 as being the point where the maximum occurs. So if we have that and we divide it by our sampling frequency, then that converts 7 to the number of seconds. So let's look at our output. So here are our two signals, and by observation you can tell it does indeed look like one signal is a delayed version of the other signal. And then here is the cross correlation, and you can tell it's pretty clear the maximum value occurs right here visually. And even though it would be very convenient if these were on the same time scale, they're not. But if you were kind of mentally looking at this, that looks like about 0.02 seconds. And if I manually observe here, it does look like about a 0.02 second delay. So the output there comes out actually to be 0.013. The maximum correlation is 0.045, suggesting that they are indeed related. Remember, our maximum would be 1, and that's going to be if there's a perfect overlay of one signal with another. What's happening here, you can tell, is that it looks to me like visually the delay is actually changing a little bit. And so that's why you're not getting super close to 1 here, is there's some jitter, a little bit of jitter in the system. So when this one perfectly aligns with this one in the sliding process, these two may not be perfectly aligned. So that jitter process is creating a problem.